Today we are going to discuss about the teaching strategies required to teach a difficult concept in an easy way. Before discussing these various teaching strategies to teach a difficult concept, we have to take the consideration of 4 points. The first one is the identification of the prerequisites, that is the identification of the previous knowledge required for that difficult concept, and also after that we have to test that previous knowledge whether it is there in our children or not. If it is not there, we have to give some sort of supportive mechanism to our children. That is, the first one is the identification and testing of the previous knowledge and to give the supportive mechanism to the children. The second one is the segmentation of the concept into sub-concepts. The third one is the identification of sub-concept in which the student is lagging. After that identification, we have to give the inputs in that particular lagged sub-concept to the children. And the fourth one, that is the most important step, is the identification whether the integration of those sub-concepts were logically integrated or not for the concept formation. This is the most important last step. So let us discuss about the teaching strategies to teach difficult concept in an easy way. Now I had taken drawing ray diagram sign conventions as the demo how to teach the difficult concept. Identified some prerequisites like knowledge regarding various terms like pole, principal axis, focus, focal length, center of curvature, radius of curvature, and the Fermat principle. These are the prerequisites. After that, if the prerequisites previous knowledge is not there among our children, we have to give the support. Now, as a second step, segmentation of the concept, I divided the concept into various sub-concepts like nature of the lens, refraction of different rays when incident on a lens, nature of the image formed by a convex lens or any lens, rules of sign conventions of F, U, V for convex or concave lens, how to solve the problems. Like that, I segmented the concept. Now, after that, I am going to give the demo how to teach a difficult concept in an easy way. Before going for any demo lesson or any teaching strategy, we have to perform an activity or we have to show an image or a video, anything else which can grab the attention of the students towards our concept. And this activity should be closely related to our concept which we are going to showcase the concept. And here I am showing one glass and two arrows are there. One glass is there. On pouring the water, we can observe the arrow is going to be reversed. And also, after pouring the water, the direction of arrow was reversed and also it was enlarged. Now we have to pose the questions to the students like how it was happened. What is the reason behind that? Let us discuss what are the reasons behind that in this lesson. Likewise, we have to pose the questions, some interesting questions that will grab the attention of the students to our lesson. Now let us discuss about the sub-concept 1, that is the nature of a lens. Here you can see when the light rays incident on a convex lens, the rays are converging. So convex lens is a converging lens. Here there is a convex lens When the light rays incident on a convex lens, the rays are going to converge at a point. So, convex lens is a converging lens. Here we have to put in the view that we have to show some animations or some more 3D pictures. We have to show more visualization, and also we have to use any activities or any interactive materials that are available in our surroundings. Likewise, we have to plan our activities in the classroom scenario so that the students can get the more experiential learning. Okay, now let us come to back to the subconcept one. When the light rays incident on a convex lens, the light rays they are converging at a point. So convex lens is a converging lens. Now we can see when the light rays incident on a concave lens, the rays are diverging. So concave lens is a diverging lens. So now I am summarizing those two concepts what I taught. Here in the summarization part, we have to give the similarities, what we taught, so many sub-concepts we may taught in each sub-concept. We used to teach so many concepts also, some small sub-concepts also. While summarization, we have to compare or we have to give the differences or similarities between those concepts, and also we have to map the concept what I taught to the present concept what we are teaching. First of all, we have to take care of that. We have to consider that one, and also we have to take care of that. Now I'm showing the difference between the convex lens and concave lens as a part of summarization. The convex lens is a converging lens and concave lens is a diverging lens. And also in the if you see the bottom part, I had given the symbol for the convex lens, that is converging lens, and also the symbol for the concave lens, that is diverging lens. Okay. Here I am putting as a part of activity, I am putting a convex lens and a concave lens, and here the students can observe how the rays are converging when we kept a convex lens in the path of the beam of light rays, and how they are diverging when we keep the concave lens. Okay, now and another thing, we have to give some convex lens or concave lens to the students and make them to observe what is the nature of a concave lens and convex lens, and they have to touch and feel how a convex lens will be, that and at the edges how it will be, at the middle how it will be, like that the students has to feel how the thicker at the middle as compared to the edges, and also they have to touch and feel the concave lens also, and also they have to identify the difference between the images what they are forming when they are visualizing some newspaper or anything else through the convex lens and concave lens. Now, for every concept, after teaching the any sub concept, after the summarization, after that we have to take a check for understanding question to how much extent the students understood that particular concept. Which lens is called as a converging lens? Convex lens. Okay. Now I'm going for the sub-concept 2, that is behavior of certain light rays when they are incident on a lens. Now, for a convex lens, the ray passing along the pole of the principal axis, that is undeviated. The ray passing along the pole of principal axis is undeviated. Ray passing through the optic center is undeviated. And here you can observe the ray passing parallel to principal axis is converging at the focus on the other side of the lens. Again, we have to take in one precaution you have to take there. For every the ray passing through the optic center is undeviated, ray passing parallel to principal axis is converging at the focus on the other side of the lens. Likewise, everything what you taught in that particular sub concept, you have to again and again you have to revise that one. Here the ray passing through the focus will take a path parallel to principal axis after refraction. Here just I am summarizing these three rays what the ray passing through the optic center is undeviated, ray passing parallel to principal axis converge at the focus on the other side of the lens, ray passing through the focus will take a path parallel to principal axis after refraction. Now I am summarizing. The first ray parallel to principal axis is converging at the focus on the other side of the lens, and the second ray through pole is undeviated, and the third ray passing through focus will take a path parallel to principal axis after refraction. Now the concave lens, ray passing along the principal axis through the pole is undeviated. Already we observed in the convex lens also the same thing. Here you can observe ray passing along the principal axis through pole is undeviated. Through ray passing through the optic center, that is pole is undeviated. If optic center, that is pole, we have to, if there are some same terminology with different words, you have to explain those also. Here you can see ray passing parallel to principal axis appear to diverge from the focus located on the same side of the lens. Here you have to make the students to identify that to appear to diverge from the focus located on the same side of the lens, and also ray appearing to meet at focus after refraction will emerge parallel to principal axis. Here you have to make the students to identify the word ray appearing to meet at focus after refraction, appearing to meet at focus, that is the important word. After that, just I am summarizing parallel to principal axis through the optics. Here you can see parallel to principal axis appear to diverge from the focus located on the same side of the lens, and through pole is undeviated, ray appearing to meet at focus after refraction will emerge parallel to principal axis. Now I am going to summarize the concept of what I taught here. We have to give the similarities or any differences. If you dealt with the different items or different scenarios, we have to compare those scenarios, and any differences between those scenarios we have to summarize that one. Here, whether it is a converging lens, convex lens or concave lens, the ray passing through pole is undeviated. Whether it is a convex lens or concave lens, first of all, you have to identify. The second thing, the ray passing parallel to principal axis, in the case of convex lens, ray passing parallel to principal axis converge at the focus on the other side of the lens. Whereas in the concave lens, ray passing parallel to principal axis appear to diverge from the focus located on the same side of the lens. Here, convex lens on the other side of the lens, in the concave lens on the same side of the lens. And here, in the convex lens, you can observe the ray passing parallel to principal axis converge. At the ray passing through focus will take a path parallel to principal axis after refraction. Ray appearing to meet at focus after refraction will emerge parallel to the principal axis. Here we have to make the students to identify the differences between convex lens and concave lens. And also one more thing, we have to make the students to identify that the image will be formed by meeting minimum 2 rays passing through the lens. That is, now we have to give a clarity to the students that Since convex lens is a converging lens, whereas in the case of a convex lens only, minimum two rays passing through the lens will be, they will meet, they will converge, they will meet at a point to form an image. But whereas in the concave lens, because that is a diverging lens, no minimum two rays will meet at a point to form a image. So we have to give the clarity that only convex lens, since it is a converging lens, it can form the real images. But whereas in the concave lens, no real images will be formed, only virtual images will be formed. We have to give that clarity, since because convex lens is a converging lens, concave lens is a diverging lens. Okay, now we have to check the for understanding. Already we taught the second concept and summarized. We are going for the check for understanding. The light rays passing parallel to principal axis will meet at a point. That point is called focus. Okay, now I'm going for the subconcept 3, drawing ray diagrams of a convex lens. First of all, to draw a ray diagram, what are the rules? First of all, we have to select a point on the object placed at a point on the principal axis. From that point, we have to draw two rays. Already we discussed, for the image formation, minimum two rays are required. They have to meet at a point, then only image will be formed. So, draw two rays and extend both the rays to intersect at a point. From that point of intersection, draw a normal to the principal axis. That length of the normal represents the size of the image. Now we can see here there is a convex lens. I kept an object on the principal axis. I selected one point. From that point, actually here you can see two rays were drawn. In the first picture, from that point, the first ray parallel to principal axis, it will converge after refraction through focus, that is on the other side of the lens. And the second ray through pole, the ray which is passing through pole is undeviated. These two rays after extending these two rays, they will meet at a point. That from that point, a normal was drawn to the principal axis. This normal represents the image length of the image. Here you can see the process. Ray passing convex lens is there, an object is there on the principal axis. I selected a point on the object. First ray parallel to principal axis through focus after refraction, and the second ray through pole is undeviated. From the point of intersection, a normal was drawn to the principal axis. This is the image. This will represent the image. Here, now I'm putting the object on the principal axis in various positions. Now, after putting in various positions, I am observing their respective image positions and also the nature of the image. Okay, now I kept the object between C2 and F2. Just to see here, parallel to principal axis, after refraction through focus, through pole undeviated, from the point of intersection, a normal was drawn to the principal axis. Now I kept the object between C2 and F2 parallel to principal axis. I selected a point on the object parallel to principal axis, the first ray after refraction through focus, second ray through pole undeviated. From the point of intersection, a normal was drawn. Here you can see this is the image. When we kept that object between F2 and C2, if the object position is between C2 and F2, the position of the image is beyond C1, and the nature of the image also you can observe real, inverted, magnified. That is, the size of the object image is more when compared to the object. So I wrote as magnified, real, inverted. Real image always will be inverted image. Position of the image is beyond C1. Nature of the image is real, inverted and magnified. Now I am putting object on C2 and selected one point, the first ray, second ray and the normal. Here you can observe, keep that object on the C2. If the object position on C2, the image position is on C1. You can observe that the object distance u, that is PC2, from PC from to C2, the PC2 is the object distance and PC1 is the image distance. The object distance and the image distance are equal. And also the nature of the image is real, inverted, same size. We have to know this situation that real, inverted and same size. That is on C2 on because the object distance is equal to the radius of curvature and the image distance is also equal to the radius of curvature PC2 or PC1. When the object is kept beyond C2 and also for the first ray and the second ray from the point of intersection normal. If the object position beyond C2, the image position is between F1 and C1 and the nature of the image is also real, inverted, diminished. Here you have to observe that in all the cases, we are drawing the same two rays. That is, the first one is parallel to principal axis and it is converging through focus. The second one is through pole. It is undeviated. In the previous cases, we observed the real images. The two rays are meeting at a point and a real image is forming. In this present situation, we can observe that the object is kept on F2 and the two rays parallel to principal axis passing through focus and the pole undeviated. Here we can observe that these two rays are not meeting at a point. If you extend these two rays, they will meet, we shall assume that they will meet at infinity. So if the object position is on F2, position of the image will be at infinite distance and the nature of the image will be point size. Okay, now I'm putting the object between P and F2, pole and focus. Now again drawing the two rays parallel to principal axis through focus and the second ray through pole undeviated. If you extend these two rays, they will meet at a point, appear to meet at a point on the same side of the lens, but they are not meeting at a point, they are diverging. They appear to meet at a point on the same side of the lens, so that this is the virtual image. This is the case at which virtual image may be formed by using a convex lens. Here, if the object position is between F2 and P, the position of the image will be behind the lens and nature of the image is virtual, erect and enlarged. This is because this is a virtual image, this is erect. You have to observe that one. Okay, now already we discussed the object position beyond C2, position of the image between F1 and C1 like that. You have to use the graph paper because the students will understand what is the relation between the focal length and radius of curvature and everything. One more thing we have to take the precaution that we have to draw these ray diagrams on a graph paper. Why? Because on graph paper we can visualize the focal length and the same radius of curvature, and the radius of curvature will be the double the focal length. If you draw that particular rays from that particular point of object, then we shall get the size of the different images and everything. If you draw on a graph paper, definitely you shall visualize that. Here you can see on the graph paper, we can see how the images are forming and everything, and the length of the image also they can visualize. Okay, now by this they can understand the relationship between focal length and radius of curvature also. The relation between the focal length and radius of curvature or is equal to 2f. Okay. Now you can see how the object position is changing. When the object position is changing, the how the image position is going to change, and where the real image is forming, where the virtual image will be formed. Like that you can observe. Again you can observe. See here, an object from beyond 2f is coming towards the lens, how the image is changing from real image to virtual image. Okay, now we can see the Colorado FET simulation. Now I'm pressing this link. I'm choosing the lens option. Here you can see if I'm changing the position of the object, how the image position and nature of the image is going to change. Here you can see here. Likewise. And also we can take a scale, and also we can measure the distance, the object distance, image distance, everything you can measure. Here what is the image object distance? 145, and the image distance is 165. And also I am putting here, this is focal length 80. On focal length I am putting that. Here you can see at infinite the image is going to form. And between focal length and the pole, a virtual image is formed, erect virtual image. And also here you can get (160). This is 160, no? Now you can measure 160. That is when the object is kept at C1, C2, again the image is formed at C1. The object distance and the image distance is the same when kept on C2. Now I'm changing the position beyond C2. See here beyond C2 how the image is going to change. Real, inverted, small size, diminished image, diminished image. If I'm putting between F1 and C1, see here how the image is get magnified, real, inverted, magnified. If the object position is F1 and C1, then the image position is magnified beyond C1 and magnified. Changing in the place of convex lens, concave lens. See here, wherever the image object position, only diminished image, virtual diminished image. Wherever kept the object, only diminished virtual images are forming. So we have this type of simulations in Colorado FET simulations. You can use these simulations. Now we shall summarize the various positions of the object and their respective positions of the images. If the position of the object beyond C, if the position of the image is between F and C, diminished and real inverted. If the position of the object is on C, nature of the image is same size, real inverted on C. If the position of the object between F and C, the position of the image will be beyond C, magnified, real inverted. In these three situations, we can observe the real images. Those are inverted also. Whereas in the fourth case, if the position of the object is between F and P, the position of the image will be same side of the lens, magnified, virtual, erect. When the position of the object between F and P, a virtual image will be formed. This is the special case we have to identify in the case of convex lens. If you see the ray diagrams of a concave lens, here you can see the ray is diverging. Image formed by a concave lens always will be a virtual diminished image, whatever be the object placed on the principal axis. We have to make sure that the students has to identify this one also. The differences between real image and virtual image. Real image can be captured on the screen, whereas virtual image cannot. And real image inverted, virtual is erect image. Now we are going to summarize the concept. Now, as a part of summarization, we are explaining the differences between the image formation between convex lens and the concave lens. Here, convex lens already we discussed when the object position between F and C, real magnified image, and also on C, where object position again on the other side of the lens on C will be the image will be formed on the same size, and also beyond C, if you keep that beyond C the object, the image position will be between F and C. Likewise, we discussed all the things. Whereas in the only the special case we have to focus that one. In the when the object kept between focus and pole, then only a virtual image will be formed on the same side of the lens of a convex lens. But whereas in the case of concave lens, what else it is? We keep the object, we shall get only diminished virtual images. In the convex lens, we shall get the enlarged virtual images, whereas in the concave lens, we have diminished virtual images. And also in the concave lens, irrespective of the object position, every time we are getting the virtual diminished images. Why we are getting the virtual diminished images? Because concave lens is a diverging lens. That's what we have to make sure that one. The students has to identify the differences between the convex lens and concave lens. Convex lens is a convergent lens, concave lens is a divergent lens, and convex lens can form real and virtual images, and concave lens always forms virtual images. Likewise, we have to make sure the differences between the convex lens and also concave lens, and also the uses of convex lens and the concave lens also applications also. Now already we explained the subconcept, and also for summarize, now check for understanding. The lens which forms always virtual and diminished images is concave lens. The lens which forms magnified virtual images is convex lens. We have to give some sort of questions regarding the table based questions which are apt for the coming examinations also. And four, we shall proceed for the next aspect, that already we learned so many sub-concepts. We have to check whether the application of these integration of these sub-concepts may be done or not in a proper way. We have to integrate all these sub-concepts. How we can do? Let us see. In the experiment done to find the focal length of symmetrical convergent lens by object distance, image distances as recorded below. Here, object distance is 60 centimeters, image distance is 20 centimeters, and 30 centimeters object distance, image distance is 30 centimeters. Already we discussed, if the object distance is equal to the image distance, that will be the radius of curvature. Then the radius of curvature is double the focal length. So the focal length will be 15 centimeters. Radius of curvature is 30. Focal length is 30 by 2, that is 15 centimeters. Without doing any calculation, on seeing the table, we can recognize the focal length and radius of curvature. Now again, what they are asking, what is the nature of the image formed when an object is placed at a distance of 10 centimeters before the convergent lens? That is, already we discussed that focal length is 15 centimeters. That is, the object distance is 10 centimeters, means the object is kept between F and P. If the object is kept between F and P, what is the nature of the image? Virtual, erect, magnified, and it will be formed on the same side of the lens. That is behind the lens. So, without doing any calculation, we can get that what will be the nature of the image and everything by application of all the concepts, sub-concepts, what we learned. No. Could you get an image on the screen for every object distance with a convex lens? But already we discussed, no, one special object distance between F and P, we can't get the real image. Okay. Now we are going to, already we discussed the sub-concepts and we integrated those sub-concepts. For every sub-concept we summarized and checked for understanding also we had done, and we integrated those sub-concepts to learn the main difficult concept, sign convention. Now, what are the basics of lens sign convention? First of all, you have to know that all the distances will be measured in the direction of incident light. Those distance may be taken as positive. All the distances measured along the direction of the incident light. Here, we have to make sure the direction of the incident light, those distances measured along the direction of incident light are only taken as positive. All the distances will be measured from the pole only, and the distances measured above the principal axis are taken as positive. Here you can see the only, here if you assume that if the object is on 2f1, we have to take O2f1, that is the distance has to be measured from the pole. Pole is O, that is O2f1, because you can see the direction of the incident ray, but we are measuring from pole to object O2f1, that is opposite to the direction of the incident ray. So object distance will be taken as negative, U negative. For any lens, whether it is a convex lens or concave lens, because we are measuring the distance from pole to object. That is, if you take the direction of incident ray like this, every time we used to measure the distance in the opposite way, O2f1. So that is the direction of incident ray. Here O2f1, if you assume the object at 2f1, O2f1, we are measuring from the pole, that is the object distance is negative, the image will be formed on the other side of the lens if it is the real image. If you assume on 2f2 image is formed, O2f2 will be the image distance we are measuring from pole to image. O2f2, we are measuring the distance in the direction of incident rays, so the image distance will be positive. That is the object distance. For any convex lens, concave lens will be negative, and we are getting the real image on the other side of the lens. So the image distance for real images will be positive. For virtual images, again, we shall get the images on the same side of the lens. So if it is 2f O 2f1 or O something like that, in that opposite direction we are going to measure. So for virtual images, image distance is negative. For real images, the image distance is positive. For the focal length, if the parallel rays parallel to principal axis, a beam incident on a convex lens, they will converge at f2 on the other side of the lens. So we shall calculate the focal length as OF2. So we are measuring the distance in the direction of incident ray. The focal length is positive for the convex lens. Focal length is positive for the convex lens. You can see here in different positions of the object positions and image positions, and how we are measuring the image distance, object distance, and the focal length. For the convex lens, focal length is positive, object distance is negative, and the image distance is positive for the real images and negative for the virtual images. If you see here, whereas for the concave lens, again we are measuring O2f1. If you assume the object is at 2f1, we are measuring the object distance in the opposite direction of the incident ray. So object distance is negative, and we are getting always the virtual images on the same side of the lens. So again, for virtual image, object distance is negative, and also for the focal length, it appears to converge at a particular point. So again OF1 on the same side of the lens only. So OF1, again we are measuring the focal length opposite to the direction of the incident ray. So focal length, object distance, image distance, everything is negative for the concave lens. This is how we have to give on the, as a summarization part. We can show the differences between the concave lens and convex lens in the regarding the sign conventions. For convex, focal length is positive. Why positive? Because we are getting the rays are converging on the other side of the lens. But whereas concave, they are diverging and they are appear to converge on the same side of the lens. So focal length is negative and the object distance is negative for both convex and concave lens. And for real images, because they will the real images will be formed on the other side of the lens, so the real image distance is positive, virtual image negative. Concave lens always forms virtual image, so image distance is negative. How to solve the problems using this sign conventions? The focal length of a converging lens is 20 centimeters. An object is 60 centimeters from the lens. Where will be the image be formed and what kind of the image is it? Find the magnification of the image. First of all, you have to observe that the focal length of a converging lens. Converging lens means that is the convex lens. Okay. And focal length of the converging lens. Focal length for a convex lens is positive. So f is equal to 20 centimeters we had taken. An object is 60 centimeters from the lens, that is object distance. For object distance for a convex lens is negative, so u is equal to minus 6. Already f is equal to 20 centimeters, u is equal to 60 centimeters we identified. Without doing a problem, we can come to a conclusion that what will be the nature of the image, where it may be found. Because the focal length is 20 centimeters, what is the radius of curvature? 40 centimeters. C will be at 40 centimeters. That is, U is equal to 60 centimeters. That is, the object is kept beyond C2. The object is kept beyond C2. Then, if the object is kept beyond C2, what will be the position of the image between F1 and C1? And the nature of the image will be real, inverted, diminished. So, the image will be formed F1 between F1 and C1 between 40 and 50, between 20 centimeters to 40 centimeters. The image distance should be there, and that is a real image, diminished image. Okay, by using the formula 1 by f is equal to 1 by v minus 1 by u, already the problem was solved. We got the image distance as 30 centimeters. That is plus value, we shall get the automatically we shall get the plus value. Nature of the image will be real, diminished, and inverted. Image forms between f1 and 2f1. Magnification is v by u. V means 30 plus here real image, no, so image distance will be positive and the object distance minus 60. That is, minus sign means real image. Which lens is used in the construction of microscopes? Light rays passing parallel to principal axis will meet at a point. The relation between the focal length and radius of curvature. Likewise, we have to put some questions, pose some questions. After that, one thing we have to do, after teaching a difficult concept, what else the concepts we discussed previously regarding the sign conventions, we have to map those concepts also to this concept. Now we discussed about the sign conventions regarding the lenses, and already we discussed about in previous classes sign conventions regarding the mirrors. Now we have to show the similarities and differences between the sign conventions between mirrors and lenses also. And again, we have to take care of one more thing while teaching a difficult concept. While teaching the second sub-concept, you have to map the first concept and integrate the first sub-concept into second sub-concept. And while teaching the third sub-concept, you have to integrate the first and second sub-concepts into third concepts. Likewise, every time we have to map those concepts and we have to prepare a summative model, something like that. Hope this will find you nice, and by using these type of various strategies you can teach the difficult concepts and they will to make the students better understanding. Thank you.